Hello everyone and welcome to Sky Scholar. In our last video, I began the analysis of various star types, beginning with objects on the main sequence. The central point was as follows. The photosphere of these stars all share the hexagonal planar lattice of the Sun. That is why these objects are on the main sequence. At this point, I wish to address the question of star formation. Does gravitational collapse of a gaseous cloud occur as is proposed in the Standard Model, or are condensation reactions involved? There remains significant confusion as to why gases do not gravitationally collapse. It is time to place this question to rest. I have treated gravitational collapse of gaseous masses extensively in these 4 videos, which you might wish to view. In treating gravitational collapse, astronomers begin by assuming that they have an ideal gas. But in the end, their problems will extend to all normal gases, as we shall soon learn. From the point of view of a chemist, let us outline the properties of an ideal gas. Such gases are characterized by 5 properties, which can be summarized as follows. First, the atoms within an ideal gas act as point sources or particles with negligible volume compared to the total volume of the gas. Second, all collisions which occur between the particles in an ideal gas are elastic. That means that the particles are not deformed as a consequence of the collision, and that no net kinetic energy is lost during the process. Third, there are no net forces between the particles, whether they be attractive or repulsive. Fourth, the particles move randomly in accordance with Newton's laws of motion. Fifth, the volume is defined by the container and pressure is generated at the walls, wherein all collisions are elastic as dictated by kinetic theory. Now let's start with the last point, namely that a container must be present in order to properly characterize the pressure and volume of an ideal gas. Of course, the temperature of the gas is related to the average kinetic energy of the motion of the particles. In setting up their gravitational collapse, all the astronomers dispense with the requirements of a container. This was reviewed when I discussed the gene swindle in this video, which demonstrates clearly that the approach genes used was without proper scientific basis. Once again, here is a key quotation from Jeans's paper. Whether we suppose the thermal equilibrium of the gas to be conductive or adiabatic, we are still met by the difficulty that the gas equations break down over the outermost part of the nebula, through the density not being sufficiently great to warrant the statistical methods of kinetic theory. This difficulty could be avoided by supposing that the nebula is of finite size and that equilibrium is maintained by a constant pressure applied to the outer surface of the nebula. However, Jeans cannot confine the outer surface of his nebula with forces originating from outside the nebular gas. Otherwise, he might as well invoke the hands of God to ensure that his equations do not break down at the edges of the nebula. Astronomers cannot get rid of the container. Otherwise, they have no means of generating pressure in kinetic theory, as all pressure within an ideal gas is generated at the walls. The interaction between particles simply transfers that pressure within the entire system. So no walls, no pressure, and no volume. Throughout their work, the astronomers have misapplied the ideal gas law. But for the sake of discussion, let's pretend that Jeans can in fact invoke the hands of God to contain his gas. The astronomers still have another problem, as collisions within an ideal gas must be elastic, and there can be no energy loss in the collisions. This, in fact, is the quality of an ideal gas which enables chemists to completely ignore the effect of gravity when dealing with gases. Ordinary gases like helium and even molecular hydrogen at ordinary pressures and temperatures are elastic. Now, what am I saying exactly? Just consider 2 helium atoms initially far apart from one another. Since they are only 2 atoms, we can ignore temperature completely and start with our 2 atoms at rest to simplify the analysis. Because the astronomers assume the collapse of an ideal gas, we can consider that the helium atoms are acting essentially like rigid billiard balls and that their collisions are fully elastic. That is to say that, during an elastic process, any shape distortion during the collision is immediately and perfectly reversed. Further, let us, like the astronomers, consider the gravitational attraction between the 2 atoms. What will happen? Well, because the atoms are experiencing weak gravitational attraction to one another, They will eventually start to move towards each other, accelerate, and eventually collide. Immediately after the collision, the velocity of each particle will be the reverse of the incoming velocity. With time, the particles will slowly come to rest once again. The process will be repeated over and over again if the system has no losses. As a result, gravitational collapse will never occur. The system is always just converting potential energy to kinetic energy and vice versa. We will set up a harmonic oscillator without losses and no collapse. This is a key point. In order to have gravitational collapse, the collisions within a gas must be inelastic. One must have the ability to permanently distort the billiard balls, for instance, in order to lose kinetic energy as heat. In that case, collapse would occur, but this would never happen in an ideal gas. Next, let us consider that many atoms are involved. Let's say several thousand, in order to make Boltzmann happy, because it takes many particles to speak of macroscopic thermodynamics. In any case, the problem for the astronomers would be that the system adopts a temperature related to the average velocity of the particles. Now, in kinetic theory, gravitational forces play no part. Why is that? The simplest answer comes from our first example with only two atoms. When dealing with an ideal gas, all collisions are considered elastic. There is no way for the system to lose energy. Therefore, there is no net effect of gravity on the position of the particles. Everything is described by kinetic theory without invoking gravity. That is why gravity is never considered in an ideal gas. In this second example, we now have many atoms in motion due to temperature. Unlike the first example, this is a thermodynamic system, and the laws of thermodynamics will come into play. As a result, the entropy of the system must increase with time in order to adhere to the second law. In reality, the system must expand over time. This acts to increase entropy as required for spontaneous processes. All the collisions are elastic, and there is no way to lose energy. This is why gravitational collapse cannot occur in an ideal gas. The fact that collisions in an ideal gas are elastic acts to completely eliminate any net effect of gravity, and the gaseous cloud continues to expand. In reality, that is actually what has been observed in astronomy, as one can gather in this paper. Most large molecular clouds have been shown not to be gravitationally bound. Yet a few are gravitationally bound. So how does one explain these cases? The astronomers try to account for this by invoking localized changes in density within the cloud, for instance. But again, if everything is in gaseous state, then collapse should not occur even within a localized increase in density. Rather, those localized increases should simply dissipate. In reality, molecular clouds are also likely to contain condensed matter, and that makes a huge difference even if one assumes that gases are present and are ideal. In this case, the gas collisions with condensed matter completely changes the scenario. In order to understand why, let us consider the Earth and its overlying atmosphere. For the sake of simplicity, we will ignore the Sun, the presence of solar winds, and the magnetic field of the Earth. As we know, the lack of a magnetic field allows a solar wind to strip the planet of its atmosphere, and we will not be concerned with this problem. Let us further assume that all gas atoms in the Earth's atmosphere behave like ideal gases. Now, these gas atoms get to strike one another as a result of elevated density and the kinetic energy of motion of the gas, which is associated with the temperature of the Earth's atmosphere. Since everything is said to act as an ideal gas, those collisions will always be elastic. We can also ignore the gravitational attraction between the gas atoms, as we noted above, since this has no net effect relative to collapse in an ideal gas. At the same time, the surface of the Earth is present, and the Earth is applying gravitational attraction on the gas atoms. This acts to pull the atoms of the atmosphere towards the Earth. Some of these atoms get to strike the surface of the Earth, and these collisions, in this case, are not elastic, even if the gas molecules themselves were acting as essentially rigid billiard balls. Some of the kinetic energy of the gas particles gets to be transferred to the Earth as heat in an inelastic process. This occurs because the surface of the Earth is not perfectly rigid. As a result, unlike the two-atom case above, in this instance, the gas particles have less velocity when their direction is reversed as they move away from the Earth's surface because kinetic energy has been lost as heat. In the end, this helps to ensure that the gas atoms above the Earth become gravitationally bound. Once again, this is because the collisions with the surface of the Earth were inelastic. In this case, the spatial extent of the atmosphere did not need to increase to satisfy the second law. Energy was being dissipated into the surface of the Earth, and that is where the entropy change is occurring. At the same time, some atoms will still manage to escape the Earth's gravitational attraction. For example, that is the reason why our planetary system is always losing helium. The helium atoms are slowly escaping the Earth's gravitational field. In reality, a second effect also comes into play here. The sun can heat the surface of the Earth, and a gas atom striking the Earth can actually gain kinetic energy as a result. This creates a steady state wherein the atmosphere maintains a certain density distribution with elevation. If the sun was not present, then the atmosphere of the Earth would simply collapse onto its surface over time as the entire system cooled. This analysis helps us to understand why some molecular clouds do not appear to expand. It is purely a manifestation that condensed matter is present in these clouds. That is what creates local inhomogeneities due to the presence of inelastic collisions. Next in this video, I wish to highlight that the self-compression of a gaseous mass under isothermal conditions is a violation of the second law because such compression results in a negative change in entropy, and all spontaneous reactions must have positive changes in entropy. In that case, no work is being done on the system from the outside. Therefore, the temperature of the system cannot increase. We have isothermal self-compression, and that is forbidden by the laws of thermodynamics. I also discussed the application of the Virial theorem to an ideal gas in this video. The problem is that the Virial theorem demands that the system in question be gravitationally bound. If that is not the case, then one is not allowed to apply the Virial theorem. The proof that applying the Virial theorem to the ideal gas constitutes a violation of the laws of thermodynamics was the result that the heat capacity for such a system is negative. Astronomers have accepted the finding without question, and as a consequence, they have long argued that the heat capacity of gaseous stars is negative. But the heat capacity of a gas is always positive on Earth and never negative. Again, the problem comes when one treats an ideal gas as gravitationally bound. This is simply false because elastic collisions exist. Such reasoning is improper relative to gravitational forces and has served to distort over 100 years of astronomy. Now let us return to our gaseous cloud at the beginning of this discussion. The only way to get gravitational collapse in such a system is to assume that the collisions are not elastic and to abandon the idea that we are dealing with an ideal gas. We have to permit that when the atoms collide, they become distorted, and now kinetic energy of motion is lost as heat, for instance. In our case, we could assume that an electron is being promoted in one or more atoms. If we then allow these electrons to emit light, the kinetic energy of the system becomes dissipated, and the system will slowly collapse as light is emitted. In this case, the temperature of the system will drop as the mass collapses, and this is allowed as photons are being emitted. The problem with this solution is that for gases at low temperatures, the velocities are too low to permit electrons to be promoted. Furthermore, in this approach, the gas would have a positive heat capacity, not a negative one, because if one would allow heat to be lost through emission, the temperature of the gas would drop in association with the drop in kinetic energy required for actual collapse. Consider a typical setting for gravitational collapse in astronomy. For instance, an isothermal nebular system. Such a system is usually postulated with a temperature of only 100 Kelvin. Such temperatures are so low that the particles making up the gas lack the velocities necessary to make the collisions inelastic by promoting an electron. Now you might think that there's another way to dump translational kinetic energy in the case of hydrogen. Instead of promoting an electron and releasing a photon, you might envision that after a collision, the molecules send some of their translational kinetic energy into molecular vibrations. Unfortunately, this is not allowed as a net process. In gases such as hydrogen at thermal equilibrium, one has equipartition of energy, as we saw in this video. Energy must always be equally distributed between translation, vibration, and rotational modes. So one does not get to dump kinetic energy of translation onto vibrational modes. In any event, astronomers use the equations of an ideal gas when addressing gravitational collapse, and such collisions in gases are always elastic. As a result, they are not able to invoke inelastic processes in gaseous clouds without first discarding the equation of the ideal gas on which their entire derivation depends. The heat capacity of a gas in the end is always positive. Those who argue otherwise relative to gravitational collapse of an ideal gas never understood the effect of elastic collisions. Their system is either an ideal gas with elastic collisions or it is not. Ideal gases never emit light, and again, this prevents all talk of gravitational collapse. The collisions are elastic. The same is true of a molecular gas like hydrogen over the temperatures which concern us. Another problem for molecular hydrogen is that it does not possess a net dipole moment, which makes any vibrational rotational emissions extremely weak and caused only by quadrupolar transitions. The hydrogen molecule itself is a very, very poor emitter as a result, as is well known by all spectroscopists. In any event, if one tries to claim that such emissions are important, then one cannot treat the process using the ideal gas law, and once again, the resulting heat capacity would be positive, not negative. As an alternative, if astronomers would allow matter to build as a liquid or solid as a starting point, all these problems would go away. In that case, when gas particles condense, there would be several possibilities to render the collisions inelastic. First, the kinetic energy involved as the gas particle collides with condensed matter or condenses onto condensed matter can be channeled into the internal vibrations of the liquid or solid. There is no requirement for equipartition in condensed matter. In this way, the collisions can become inelastic and condensation can occur. Alternatively, when condensation reactions occur, it is also possible to emit light, as we saw long ago now in this video dealing with silver clusters at low temperature. Chemical reactions can come into play, and this greatly increases the means by which condensation processes can take place. To summarize, gravitational collapse of gases simply does not occur. Gases expand to fill the void because at the temperatures of space, all collisions are essentially elastic, and the second law of thermodynamics governs. Because the collisions are essentially elastic, the gravitational forces between particles have a completely negligible effect. Once again, the force of gravity is never included when one deals with ideal gases. This is a fatal blow not only to the entire field of stellar evolution, but also to the possibility that black holes could ever be formed from the gravitational collapse of a gaseous mass. The only solution for astrophysics is to accept the reality that stars are comprised of condensed matter. Such stars are built from the slow aggregation of atoms during the inelastic collisions which take place during condensation. It is extremely likely that the stars are formed from condensation reactions which begin with the formation of simple hydrogen clusters. The capture of a simple free proton can begin to seed the process, as I first reported long ago in this lecture. A hydrogen atom combines with a proton to build a trihydrogen cation. In fact, such a molecule has been detected in an astrophysical setting, as has been mentioned in this paper. It is clear from the discussion today that emissions from star-forming regions are likely to arise as a result of chemical processes involving condensation reactions. The temperatures in these regions are simply too low to argue otherwise. That was the lesson also for the silver clusters, as we saw in this video. In any case, here is a list of important papers with respect to the hydrogen cluster formation. A central feature is that the presence of charge on such a species acts to stabilize the clusters against sublimation, and that is key to help small clusters grow. So the idea is that from small clusters, a star will eventually form. A star is likely to be the product of condensation reactions, first through simple clusters, then building to ever larger sizes. Throughout the process, stars are made from the buildup of condensed matter. Gaseous collapse never happens, but rather gaseous atoms and molecules just condense more and more onto the cluster. One thing is certain, the astronomers never properly understood the ideal gas law. As such, all talks of gravitational collapse of an ideal gas manifests a lack of understanding of fundamental principles or a complete disregard for the laws of nature. Gases do not gravitationally collapse and have never been gravitationally bound. As a result, it was completely improper for the astronomers to apply the Virial theorem to gases. In reality, the volume occupied by a free gas cloud must always expand as dictated by the second law. This is true not only for theoretical ideal gases, but for all gases of relevance to astrophysics, because over the temperatures of interest, all gases are restricted to elastic collisions. Stars are simply not gaseous plasmas, and once again, there is absolutely no evidence that the body of the Sun can exist in gaseous form, even as a plasma. Everything about the Sun points to condensed matter, including helioseismology and the solid body rotation of the solar core. As a result, it is time to abandon ideas which have hobbled scientific progress for 100 years. Gaseous stars have enabled leading authorities in astrophysics to pollute science with such fantasies as black holes and big bangs. Again, the stars are condensed matter, and metallic hydrogen is by far the best candidate to assemble such structures. This radical idea changes absolutely everything we understand about astrophysics. Well, that is all for now. If you enjoyed the video today, promote the channel, mention the videos to your friends and to your local astronomy club, support me with a like, and subscribe for more videos as we look more closely at the Sun, the stars, and beyond. Comments are welcome down below, and I'll see you soon on the next video.